Okay, so chapter 14, we have two topics really to cover in this chapter: building multiple regression models and analyzing the multicollinearity. So, although there's many topics in this chapter, and I wanted to point that out in case down the road you do need nonlinear regression methods or logistic, that's when your outcome variable is a 0, 1 itself. So it either happens or doesn't happen. Then this chapter can tell you more about that. But for our purposes, what we want to focus on is building the best regression model, the one that's predictive, that uses our variables in the best way possible, and also to check it out to see if we have any issues with our data being input into a model. Okay, so model building. So I have some data here just to explain what it is before we look at it. So it's about crude oil, and we want to predict the world production of crude oil based on 5 predictors. We have U.S. energy consumption, gross U.S. nuclear electricity generation, U.S. coal production, total U.S. dry gas production, and fuel rate of U.S.-owned automobiles. That data looks like this. It is in Excel, so we have it ready. And we have our regression results. So let's go ahead and check it out. So here is the Excel data, and our Y variable, crude oil, is here, and then we have those 5 predictors. If we were to throw them all into a regression, so let's go ahead and check it out. So here's our outcome, followed by all of the predictors. So we grab them all at once, and labels included. We'll go ahead and include all the plots, and we get the following. So in terms of the statistics around this model, at first you look at it and you're like, wow, we've explained 90% of the variation in crude oil. We have standard error 1.21, which I'll have to look at the units to see how much that varies around the response plane. We have 26 observations. If we go down here to our model, this tells us, again, our null hypothesis is that beta 1 equals beta 2 equals beta 3 equals beta 4 equals beta 5 equals 0. And the alternative, at least 1 beta, is not 0. And we reject the null because significance F is very, very small. But when we come down here and check out the p-values, we have independent tests for each of these. Right? So here we have beta 1 equals 0, beta 1 not 0. This one, the hypothesis beta 2 is 0. The alternative is beta 2 not 0. Fix this one. Here we have beta 3 is 0. Alternative is that beta 3 is not 0. Next, beta 4 is 0. Alternative, beta 4 is not 0. And the last one is beta 5 equals 0, or beta 5 is not 0. When we look at the p-values, you'll notice only one of them leads us to reject the null, right? That's for x1. All the others we fail to reject. So it begs the question, if you wanted to provide somebody with a model that predicts crude oil production, would you give them the equation that has all of these predictors in the model, such that they would have to go out and find all of these pieces of information? Or do you want to try to create a more streamlined, parsimonious model that only has in it what matters? So if that is the case, and that's not always the case, sometimes people want to know, how does everything affect the outcome? Then you would give them a model with everything in it. But if your purpose is to give them the best model, most predictive model with the least amount of variables, then we want to build a regression model that only has those that matter. That's what we want to do. Okay, so let me go back to the PowerPoint. Okay, so this is our result. So you could, brute force-wise, try a regression model that has each single predictor in it alone. Then you could try each pair of predictors, each set of 3, each set of 4, and then as we just did, all 5, right? And you can see here, this just shows you how many possible combinations you would be trying. And it would take a lot of time, and then you would also probably have difficulty comparing all the models when you had them all complete. So we have some approaches that will help us build models instead of this brute force method of trying every single possible model. So this chapter lays out kind of 3 smart ways to do it. So it's stepwise regression, which interestingly enough, I think is the kind of the gold standard of what gets used, because a lot of our software these days will do it. And as you'll see, it's not the easiest to do yourself if you have to do every step. Forward and backward selection and elimination are the ones that I would recommend if you have to create a model yourself, that your program won't run through the steps for you. And you'll see everyone, I'll tell you, usually likes backwards elimination the best. Okay, so why? Well, let's get to what each of them, what are the procedures for each of these different approaches. So stepwise is this step-by-step approach where we're going to put in a variable and we're going to try them until we find the most significant one to put in the model, and we're going to put it in. Then we will add a second one, keeping the first one in the model. And we'll see if we find another one that's also significant along with the first one. And based on the R-square, changes in R-square, as well as the significance of our predictors, we determine whether we want to keep a second variable in the model. And then if we do, then we move to keeping a third. And we keep doing this iterative process until no more variables are significant when they come into the model. And then we stop. So it's still tedious, I will say. Okay, so let's check it out. So you have to try at first running every independent variable on its own. And as such, we get the following information. So if this is crude oil as Y, then you try variable 1 alone. And this is the T ratio down in the coefficient test and the R-square of the overall model. And you do this for each one of your predictors independently, right? And you create this table. And you see which one kind of has the biggest bang for its buck, right? And that's going to be variable 1, which was oil production. Okay, so then we move to kind of step 2, where we keep, not oil production, energy consumption, I'm sorry. So oil production is our outcome. So we keep energy consumption in the model, and now we try it paired with another variable. So we try energy consumption paired with nuclear, energy consumption paired with coal, energy consumption paired with dry gas, energy consumption paired with fuel rate. All right, and then we check it to see if there is a significant T or coefficient test. So it's got to be it has to be significant, and of those that are significant, which one is the highest T ratio, and then also you can also determine it based on, of those that are significant, which one has the highest R square. Now these should tell you the same information that you should add it. They should each show you be the highest of your options. So you take the highest of your options and you keep them. And now we continue because we had a significant second variable that we put into the model. So now we continue and we run. So we have energy consumption, fuel rate, and nuclear, and then energy consumption, fuel rate, and coal, energy consumption, fuel rate, and dry gas. And when we check the significance of these newly added variables, and if any of them are significant, we would pick the highest significant one, and we'd check to make sure that it also should have the highest R-square of the model. But if you were to actually try this, you would find that none of these are significant. The p-values are all over 0.05 for the newly added variable. So no new variables will be added to the model. Okay. So in some programs like Minitab or SPSS, the way this looks in terms of outcome is on the next slide. Here. So it shows you it went through 2 rounds. It determined what to add, so energy consumption, and it kept it in the model. And then it shows you what to add next, which is fuel rate and the p-value. And then it stopped because it did not find a third variable that was significant to add. So that would be the end of stepwise, and this would be your final model with 2 x's, 2 predictors predicting oil consumption. Okay, so that's one approach. And the trick is, though, there is one hang up in stepwise. It could be when you get down the road, especially if you're adding a lot of variables, it could be that your third variable is significant, but when it gets added, a third variable, it kicks out and makes some previous variable not significant. So then you get in this quandary of what to do. So the rules say that you would add the next variable and take out the one that has now become not significant and not try it again. So it does make it a little bit complicated. So on the other hand, we can go to forward selection. Forward selection is just like stepwise, but once a variable is entered into the process, it is never dropped out. So it works the same way. So you find the most significant predictor, add it in, and then continue to iterate, pairing it with the next predictors, and you find the most significant, highest t-value one, add that to the model. And then if you get to like the third or the fourth, and all of a sudden it's significant, but it kicks out the significance of a previous variable, it doesn't matter. You leave it in, add in the new one, and keep going. So you could end up with non-significant variables using forward selection. It's just how it happens. So those are 2 approaches, and some of it is a little bit, they call it, satisficing. So we only have so much cognitive power to figure out what we should do. So if it's working pretty well, let's just use it. That's what these approaches are getting at a little bit. So let's go to this third approach. Now we like this one because it always ends with only significant predictors in the model. So here we start as we did earlier, and we start with the full model. We throw everything into it. And then you start to cut the most non-significant predictors until you're left with only significant predictors. So we have an example here from the text. So for instance, if we ran everything as we did, and we'll check it out here on the Excel sheet in a second, you'll go to the coefficients. Okay, we have our coefficients. And really you go over here to the p-value, and you find the worst p-value and drop that variable out of the model. And then you rerun it and you find the worst p-value and you drop it out of the model. And you continue to do this. So here we have another one, coal gets dropped out of the model. And finally, we end up with a model with only significant coefficients, and we're done. Great. So in looking across our 3 steps, now they can, each of them, give us a different final result in terms of a model. But we have at least smartly created a model that has, in some ways, the best predictors in the model. Okay, so let's check it out. So again, here we would go to our p-values for backwards, and we would find the worst variable, x4. Then we have to go back to our data sheet, crude oil, and we have to get rid of x4. So you can figure out how you want to do this. Again, when you're running the regression model, you have to keep all of your x's together, right? So I copy it over and then delete the one I want to get rid of. All right, and then run it again. All right, so our y stays the same, and our x's move over here. Okay. All right, and then again, we go straight down. We got a good model, but here we have our p-values. We go straight to the p-values, find the worst one, which is here, x2, and we're going to get rid of x2. All right, so let's go back to our data. I'm going to copy it. Get rid of x2. And now we run it again. And we run it again. Okay, so now we have our model, and just like in the slides, we see we have one more variable to cut. We go over here, we copy it one more time, we get rid of x3, and we run the final data analysis. So we are left with x1 and x5. We have 2 significant variables in the model, and now we're ready to actually look at our overall model statistics and evaluate it. Interestingly, when you get it down to this stage, you will see that our R-square and our adjusted R-square should stay pretty high. It should be up there at just about the same level as we started, because we've removed some of the penalty because we have a lot less predictors in the model. All right, so that is building a smart model, and then we can come up with the equation. So we have y hat equals our y-intercept plus the coefficient for beta 1 for x1 plus the coefficient times x2. And we have our predictive model we can share and then predict the amount of crude oil consumption. Okay, so that's it for model building, and we have one more section on multi-collinearity.